Now for the proof of the third part, in which we have to show that there exists a continuous function with compact support G, complex valued, such that the norm of f minus g is less than or equal to epsilon. So here we will use the second part. So by the second part we can reduce to the case of step functions, meaning that f is a step function, and then further to the case when f is the indicator function of a box B. So using the same kind of linearity trick that we used before, using triangle inequality, we can reduce to this case when f is simply the indicator function of a box. So then choose an open elementary set, open box B prime containing B, such that the measure of B prime is less than or equal to the measure of B plus epsilon, which means that the measure of B prime minus B is less than or equal to epsilon. Here I would also like it to contain the closure of B. So our box may not be closed, but we can arrange so that B prime contains not only the box but also its closure, and then we'll still have this inequality because the measure of B is the measure of B bar. So we can assume without loss of generality that B is a closed box, and now we have chosen an open box B prime containing this closed box B, and now I'm going to use Urizone's lemma, which states that there exists a continuous function G from RD2 to the set 0 1. So it takes values only in the interval 0 1, such that G is equal to 1 on the closed set B bar, B closure, and G equal to 0 on B prime complement. So this is about separation of disjoint closed subsets of RD. This is a closed set and this is a closed set. So Urizone's lemma states that there exists a continuous function which is 1 on one of the closed sets and 0 on the other closed set. So we are going to use this to determine our G. So in fact this is the G we want, because the norm of chi B minus this G and the L1 norm is bounded above by the measure of B prime minus B bar, because otherwise G is 1 on B, okay, and then the only place where G is not equal to 0 is then outside B, but then it is again 0 outside B prime. So since G takes the value between 0 and 1, it is less than or equal to 1 times the measure of the set on which G is strictly between 0 and 1. So this is what we get, and this is less than or equal to epsilon. So this implies that we have f minus g is less than or equal to epsilon for any step function f, and this implies again by 2 that f minus g is less than or equal to, so here this g is not the same as this g, so let me write g1 and g2. So here there exists a continuous function with compact support g prime or g1 such that this happens, and here there exists a continuous function with compact support g2 such that f minus g2 has L1 norm less than or equal to epsilon when f is a general step function, is a general L1 function. So we have reduced it to various cases, and we have shown this all the three parts of the preparatory lemma, and now we come to the proof of Lusin's theorem. Proof of Lusin's theorem. So let us fix epsilon greater than 0, and by our preparatory lemma for each n we can choose a continuous compactly supported function fn from Rd to C such that the L1 norm of f minus fn is less than or equal to epsilon by 4 to the power n. So you will see why we have chosen this epsilon by 4 to the power n, but this is our function g, which is chosen, we can choose it to be continuous with compact support, and our epsilon in this case is epsilon by 4 to the power n. So this g, since this depends on n, we have renamed it as fn, and of course we would like our fn to converge to f, so rather than using g's we are using fn's. And now by Markov's inequality, we have that the measure of points in Rd such that fx minus fnx less than or equal to, greater than or equal to 1 over 2 to the power n. So the measure of this set is less than or equal to, so this is our lambda here, so it is less than or equal to 1 over lambda times the L1 norm of the function that you are choosing. So this is nothing but 2 to the power n times the L1 norm, and because we have chosen this L1 norm to be less than or equal to epsilon by 4 to the power n, so then this is 2 to the power n times epsilon by 4 to the power n, which is equal to epsilon by 2 to the power n. So now let me denote this set by an, and let A be the union of an's n greater than or equal to 1. So this means that the measure of A is less than or equal to the sum epsilon by 2 to the power n, n equal to 1 to infinity, and this is less than or equal to epsilon. So the measure of A is less than or equal to epsilon, and let's see what happens outside of A. So outside this set A. So if x belongs to A complement, then we have fx minus fnx is less than or equal to 1 over 2 to the power n for all n greater than or equal to 1, and this implies uniform convergence of this function sequence fn converges uniformly to f outside A, and so this is our required set outside of which there is uniform convergence of fn's to this function f. This also implies that f restricted to A complement is continuous because all these fn's are continuous. So uniform convergence of continuous functions gives you a continuous function. So this means that f, when restricted to the complement of this set A, is a continuous function, which proves Lusin's theorem. Now we put an equivalence relation on L1 functions as follows. So we write for two L1 functions, L1 functions f and g, we write f is equivalent to g if and only if f agrees with g almost everywhere. So again with respect to the Lebesgue measure. So we are still on RD, and with this equivalence, so first of all one has to check that this is an equivalence relation. It's quite easy to check that this defines an equivalence relation. So it's almost immediate from the definition of the the relation that it is an equivalence relation. So now we take the equivalence classes of functions, L1 functions with respect to this equivalence relation, and so we write the equivalence class of f. So for f in L1, the equivalence class of f is the space of all L1 functions such that f equal to g almost everywhere. So rather than using a new notation for this new space of equivalence classes, we continue to denote the space of equivalence classes f for L1 functions as L1 of RD. So rather than using a new notation, we still write it as L1 RD, which actually should have been written as L1 RD from our previous notation modulo this equivalence relation. So rather than writing it as modulo always, we are going to write it as simply L1 of RD. Now with this new space, we have a following lemma, that the map D1 from L1 RD cross L1 RD to 0 infinity given by D1 of f comma g actually these are equivalence classes, but it's not going to make any difference. So this is simply the difference of the L1 norms of f and g. So one has to check that even if you take f prime and g prime in the same equivalence class, you will get the same result, but this is an obvious statement to make. So we have that first, that this is a well defined function, is well defined, and it defines a metric. It defines a metric on L1 RD. So by the properties of the metric, we just have to check for positivity and triangle inequality and reflexivity. So I leave it as an exercise again to check that this is true. Check that this is true, which is that this defines a metric on the L1 functions after you have modded out by the equivalence relation. So the importance of this metric comes from the next theorem, which is called the Rees-Fisher theorem. Rees-Fisher theorem, and it says that L1 RD equipped with this metric D1 is a complete metric space, which means that all Cauchy sequences converge. So we also know that additions of L1 functions are in L1, and scalar multiplication by complex numbers of L1 functions is also in L1. So in addition to being just a complete metric space, we can say that it is a complex vector space. So here L1 RD is a complex vector space which is complete in the L1 norm. So this is a complete normed space, which means that L1 RD is a Banach space. So remember that a Banach space is a complete normed space. So L1 RD with the L1 norm is then a complete normed space, and so a Banach space. So this study of Banach spaces, so let me just remark here that the study of Banach spaces leads us to the field of functional analysis. And in particular the space of L2 functions on RD, which is defined as the space of measurable functions, complex measurable functions, such that modulus f square belongs to L1 of RD. This is a so-called Hilbert space, So I haven't defined the norm here, but I just want to mention that this L2 space and L2 space is has a special importance in the space of these kinds of Banach spaces of LP functions. So we can also define LP of RD, which is the same class of complex measurable functions such that the pth power, so here p is a real number greater than 1, and this is also a Banach space. So all of these LP spaces are Banach spaces, but in particular this space L2 is the only one which is a Hilbert space. So all these things are topics that are taken up in the field of functional analysis. So we don't have time to go into all these details, but the Rees-Fisher theorem is a very fundamental first result in this area, which says that L1 RD is a Banach space.